بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. I am Saddam Al-Zami, research scientist today at Sadaki FUBM Joint Research Center for Artificial Intelligence, and I will be moderating today's session. Welcome all attendees, and thank you very much for attending our today's session. This webinar is organized by SADAIC FUBM Joint Research Center for Artificial Intelligence and facilitated by KICS. Today's webinar entitled Tokenizers for Arabic Text Classification and Empirical Study, and our today's speaker is Dr. Irfan Ahmed. Dr. Irfan Ahmed is an assistant professor in Information and Computer Science Department at King Fahd University of Petroleum and Mineral, and he is also a fellow at SADAIC FUBM Joint Research Center for Artificial Intelligence. He received his PhD in Computer Science from TU Dortmund University, Germany in 2017. Dr. Ahmed's research interests mainly focus on machine and deep learning and natural language processing. Dr. Ahmed has published several articles in peer-reviewed journals and international conferences. In addition, he has authored 2 book chapters and 3 US patents. Kindly be informed this session will be recorded automatically, and if you have any question, please type in your question in the question box or raise hand, and your questions will be answered at the end of the presentation. Dr. Irfan, please, the floor is yours.
Thanks much. So, okay, thanks so much for the opportunity and for the introduction. So, today I'm going to present the topic is Tokenizers for Arabic Text Classification and Empirical Study. So the topic here is mainly related to the natural language processing area of AI, and it does touch on machine learning and deep learning, but mainly it's about natural language processing. So I'll first introduce the topic. What do we mean by tokenization, and why do we need tokenization for Arabic text classification, or generally speaking any NLP task? Then we'll speak about different tokenization schemes, how we can do this tokenization. And then once we present a number of tokenizing schemes, we'll evaluate them. And there we have 2 major ideas of evaluations. One is unsupervised evaluation, and the other one is evaluating on the text classification tasks. So we have several text classification tasks, and we'll try to evaluate those tokenizers to see if getting all of them are equal or are as good as others, or there are some other insights we can learn from that. And finally, we would like to conclude and present some possible future works. So yeah, the point, before I move forward, it's important to acknowledge that this presentation is mainly coming from a paper we recently got accepted with my students, Zaid Al-Yafe, Majid Shaibani, and Mustafa Ghalib. So this work is based on that paper, which got recently accepted in neural processing patterns. Good. So the question now is, what is tokenization? What is tokenization, and why do we need it in natural language processing? So the main idea of tokenization is natural language processing. You are doing a task. For example, you want to classify text, you want to do question answering, you want to do machine translation, but the input text is just a sequence of words or characters, depending on how you look at it. So we need to break down these sequences into meaningful units, or at least into units, right? Whether meaningful or no, that's again something interesting that we'll see very soon. But definitely we want to break down these long sentences and paragraphs into small units, right? And these small units represent that text. It's called tokens. Those tokens are, again, it could be, for example, we'll see very obvious choice for a token. It could be a word as a token, right? But then to do something as a natural language processing task, such as machine translation, question answering, text classification, we need to encode this as features in our machine learning model or deep learning model. So what we do is basically each of these tokens are represented as some integer sequences, right? Numbers. And later on, what we do is in the model approaches, we try to map these individual tokens into some dense vector to have some meaning. In a sense, we try to encode some meaning to those tokens, which could be words or whatever representation we choose, right? And again, as I said, in most of the languages, and specifically those languages which use white spaces as a boundary, a word boundary, using words is the most obvious choice, and people have been doing this since long, right? So just split the word text into words, sequence of words. And this is also sometimes called as white space tokenization, but you have to keep in mind that we can also do word tokenization even if languages, especially East Asian languages, you have which does not necessarily do white spaces, right? So we can also do word space tokenization even if you don't have white spaces. But for many popular scripts like Roman script or Arabic script, we have words, white spaces are obvious, and we can use that. So this is just a quick example in English. So it's a panogram which says the quick brown fox jumps over the lazy dog, right? And it's assuming that this is one complete sentence, we can just break down based on the white spaces. So the becomes a token, quick becomes a token, brown, fox, and so forth. Every single word becomes a token. And then once we have split this into tokens, we need to basically represent those words or tokens into some form of, let's say, a vector, which can hopefully encode or some sort of meaning to that, right? And that can later be used for whatever task you're doing, like text classification. So yeah, as we said, the most obvious choice is words, but there are some issues with using words as tokens. So one of the most common issue is it leads to a huge vocabulary size. So assuming you have, for example, in many NLP tasks, you have corpus, big corpuses with hundreds of thousands of running words, or if not millions of running words. Now, if you map them into unique words, unique word tokens, you might easily end up with 500,000 words or few 100,000 words, right? So it's a huge vocabulary size, and then once you're going to represent that into a dense vector, you need all that data to represent all those different words, right? Another major issue with using words as tokens is the issue of out of vocabulary. So what if you compile a list of unique words from your training corpus, and in your test data, you find new words, which is quite is common to experience, right? So there are some tests done in different research for English. It says, for example, that if you have new text, unseen text, the new vocabulary increases approximately by the square root of the running number of words. So the point here is that it's very obvious to expect that you will have new words in the test data which you have never seen in training. What do you do about that? So that becomes a big issue to deal with. Of course, there are approaches like mapping them into unknowns, tokens, and stuff, but that does not really solve. It does solve the problem of running the system, but it does not really solve it that in a sense that you don't know what that word is, right? So the point here is that yes, words are very obvious and straightforward approach, but it's not the most efficient representation. So there are other approaches. So the other extreme to word being as token is to use characters as token. So just split the text into individual piece of characters again, right? So for example, in English, you have A, B, C, and C can have some digits, some special symbols, and that's it. So this is the other extreme of what you can do. Of course, it has its benefits. One of the benefits is the vocabulary size is almost fixed, right? You never see a new character, right? If you have a script, you know what characters to see. So that's it. So for example, in English, it's 26 different characters. In Arabic, it could be 28 or 29, depending on how you count it, right? But then also you will never have the situation of a new word coming out, which is out of vocabulary, because those words are always constructed with the known characters instead. So that also problem is solved. But then the challenge of using character is, of course, one obvious challenge is characters by itself might not encode meaning. So if you're doing an NLP task and you need to understand meaning in long context, long sentences, right? So how efficient is it to encode that meaning through character sequences? Because now your input becomes a long list of tokens. So for example, if you had a sentence which you input to your model, that sentence had 10 words, your token was a sequence of 10 different embeddings. But now if you're using characters, that 10 words now can easily become 50 or 60 tokens. And now you have this representation of 50 different tokens inputting it. And how do you map or how do you model that long-term context of meaning and other stuff, right? What you would ideally like to have within NLP tasks. So again, there are two different extremes. Between these two extremes are what we call the subword tokens, words tokens which are at the level of smaller than a word, but generally bigger than a character. So we call those subword tokens, and there are many different approaches how to come up with the subword tokens, right? So here we are listing down 6 different possibilities of tokenizing Arabic text. And many of them are common in nature. You can use it for any other script, but some are very specific to Arabic. The top 3 are very commonly used in literature, and the bottom 3 basically I would not say we came up with it completely new, but at least we tried these new ideas of tokenization NLP for Arabic, which people have not been reporting, at least in the published literature. So the first one, as I just said, is just what tokenization gets in the context of Arabic. What you do is you look at white spaces and you just split the text into words, and then those words becomes the token. Characters, I just said, each and every single character becomes a token, so you just split based on every single character. Then there is a very popular approach, which is currently used, I would say one of the most popular approaches, the sentence piece tokenizer, as a whole umbrella of it. And then within that, you also have byte piece encoding, which is very popular in deep learning architectures, right? And it's basically an instance of a frequency-based tokenizer. What you do is initially you split everything to characters, but then you start merging them. Wherever you see that 2 characters or 2 subwords are very frequently occurring, you merge them into one bigger token. What happens as a result of that is that those words which are very frequently occurring in your text will have them intact as words, but those which are very infrequent combinations of characters or subwords, you split down into smaller units. So this is one thing. And also because you have the smaller units in your vocabulary, if you have new words which you have not seen, you can always construct them based on these smaller units. So it has a lot of benefits in that sense. So this is what we call the byte pair encoding as an instance here. Then we have this 4th one, which we are evaluating new, at least we've not seen much work on this area, is what we call the morphological tokenizer. Now, morphological tokenizer is utilizing the morphological knowledge of the script. So for example, in Arabic, you have these stems and prefix and suffixes, and what you're going to do is you're going to break down them based on the morphology of the language, and each different affix or the stem is treated as a unique token. Now, it has its own benefits in a sense that, of course, your vocabulary size does not increase a lot, because in Arabic, we all know that it's very inflectual language, right? So morphological is very rich, so you get many different forms of the word. For example, kataba, yaktubu, taktubu, you know better than, right? Most of you know better than me. So you can have a lot of words, but it has, at least in the core of it, it's the same meaning, right? So morphological based tokenizer has this advantage that it can at least go back to the stem of the word, and all those different forms of the word maps to the same single token, and then those different prefixes or suffixes like sa and ya and ta, depending on what gender or the singular or plural, you can use them as affixes. So that's the idea of morphological tokenizer. Then we have our 5th one, which is what we call the disjoint letter tokenizer. In literature, it's also called as part of Arabic words, forms, right? In NLP, it's not used a lot, but if you come to, for example, OCR, it's also used somewhat. So this idea here is that in Arabic script, you have some letters, even though they come within a word, they force the word to split into parts of word, in a sense that it does not join to the next word. Example of that being da, and wow, and other different characters. We have 6 different characters in Arabic, which does not join to the next character, even if it comes to the within the same word. So the idea here was, what if we use that idea of those character sequences which join together in a word being a single token, and we split the word based on those number of components we have. So that's the idea of part of Arabic words. Again, having that idea benefits from the fact that because it's splitting the word into subwords, and there is a mechanism, you're doing it based on some knowledge of the script, so your unique vocabulary will not increase as much as you have words. So the vocabulary size will be limited if you compare with the case of word tokenizer. And also, there's a high possibility that you have a new word which you have never seen, but you might have those small parts of words which can be used to like join together to come up with this new word. So this is another possibility that has a benefit, at least theoretically, that this joint letter tokenizer can do. Finally, we tried another idea, which is what we name it as stochastic tokenizer. The idea that what if, and this was also the idea to use it as a baseline to see or benchmark other tokenizers.
what if we, instead of following any specific idea, let's randomly split the words into tokens, randomly, without any knowledge of the script or without any really procedure. For example, in sentence piece, we are counting the frequency of bigrams or words, characters or subwords coming together. Here, no, we are going to split the words randomly. So let's see how does it as our baseline. So this idea was what we call the stochastic tokenizer. So these are the 6 tokenizers. So in this particular work, what we're trying to do is we are going to evaluate these 6 tokenizers on a number of Arabic text classification tasks. So we have some tasks which are related to sentiment analysis, binary classification. We have something based on news text classification, which is kind of 5-class classification problem. And then we have another task of text classification, which is a poem meter classification. In Arabic poems, you have what you call the meter. There are 16 of them. So in the data set, we have 15 available. So we try to see that given a verse of poem, which is what's the meter of that poem. So it's another 14-class classification problem. So we're going to use these tokenizers and compare their performances on these different tasks. And we have a number of data sets to do that. Before going further, this shows an example, an illustrative example of the idea of different tokenizers. So, yeah, I'm sorry. Yeah, thanks much. So, for example, the first one, the text is Nasrun Hakim lahu sir qatim wa zu shanan azim. So, again, if we are speaking about words, you are using every space where we are replacing it by this underscore visually to show that you're splitting the text into words. The second example is about the character tokenization, where every character is basically a token, right? So we just split the text into characters. The third one is the sentence piece. So assuming that Moon and Saw was not coming too frequently in the text, they were still separated. Hakim, assuming it was coming a lot in the text, so it's still intact as a single word. The Lahu is there because coming. This is just an illustrative example to show that those sequences which are not very common are split, and those which might be common might still remain as a word, or at least some sequence of characters, if not a complete word. So this is the idea of the byte encoding thing, or this sentence piece thing. So then the fourth one, we're speaking about morphology. So for example, you can see that most of them is similar to the word tokenizer, but lahu, so la and ha is split because of the morphology, and wa zu, so wa and zu is again split. And again, it can depend on the text, it can split based on the affixes available in Arabic. Of course, for this tokenizer to work, also you need to have this tool which has learned the morphology of the Arabic, which is sometimes challenging if you are using, let's say the tool is trained on a classical text and using very modern text, new words, how do you decompose them based on the morphology? Or if you're using standard Arabic and you're using it to, for example, split the text of Twitter data, which is not very standard Arabic. So those type of challenges do occur there. The fifth one, which is the disjoint letter tokenizer, you can see that each token is a sequence of connected characters. So you can see here, so qati'un, qaf, alif becomes one token, ta and ain becomes another one. And wadu, it becomes 3 tokens because each one of them does not connect together, and so forth. And last one, it just shows an illustration that randomly you just selected some splitting points and you split them into tokens. So these are the illustrative examples for the 6 tokenizers we are adding. This shows another example, and here it shows that what can happen, you can see in the text, you have some black boxes, small boxes, which shows that, let's assume that this running text was there on the test data. What can happen for the word tokenizer is maybe those 3 words were not even available in the training. So it has to deal with that as unknown words. So 3 black boxes there. Sentence piece mostly will not have unknowns, but again, you can see that maybe a shabab was very common, so it's still there. But for example, Suna is also very common, maybe, but maybe Sabeh was not common. It's split into different subwords and so forth. Again, other examples, stochastic disjoint, again, you can see some splits, but mostly you don't see unknowns much. Characters, definitely you don't see any unknowns because it's all the unique characters, you'll always have it. And morphological ones, also you might have some words which are still unknowns. So this is just another illustrative example for different tokenization schemes.
Now, before moving to evaluating them, these are some of the ideas or some properties we could find or we can discuss about different tokenizers. So one of the things is the coverage. So in case of coverage, we are speaking about does the tokenizer leads to out of vocabulary or no? Does it cover all the text unseen texts? So of course we know character is the one which has complete coverage, and also sentence is almost every time we have complete coverage, right? Because it's trained based on it starts with character sequences. So coverage for these two will be there. Others will not guarantee you coverage, so there might be unknown words there. Similarly, which of those tokenizers uses the knowledge of the script morphology? So we have morphological tokenizer, as the name suggests, and also disjoint data. You need to know the script knowledge to tokenize those, right? On the other hand, for example, stochastic or sentence piece, they are completely agnostic, language agnostic. You don't need to know the language to use those tokenizers, right? Similarly, what about the randomization? So randomization, we have only one, which is the stochastic one, which works completely random. A language agnostic character, words, stochastic, and sentence piece. These are mostly you can use without knowing the language, right? Any language can apply to almost every time, yeah, except word, which is a bit. We can't say completely language agnostic because again, if you have some other languages which does not have white spaces, you might have to prepare some algorithms to do that organization. The last property is the granularity level. So the character one is very fine grained, so you have many tokens. So input becomes a long sequence in that sense. And the word is the most compact, so it has very coarse grain. Morphology is almost similar to word, a bit more fine, but the others are, you can say, subword level, so it's medium. So these are some of the properties of different tokenizers. Now, how do we do the evaluation? So we have two different ideas for evaluation. One of them was unsupervised evaluation, and we have some attributes. For example, we look at how much is the speed of tokenization. Speed in terms of training, preparing from the training set, the tokens, and then applying it on the new set. So that's to inference or whatever it comes. So those are one aspects to evaluate different tokenizers. The rate of unknowns, how many unknown words comes if you are looking at some running text, depending on the vocabulary size. And then the compression factor is how much basically tokens it creates for every unique getting sequence. So if the maximum is you split everything in characters, so how much you're compressing. So word in a sense will have a good compression factor. Character tokenizer will have a very bad compression factor. It does not compress a lot. So we'll see something more about that. And to do this type of evaluation, we use that corpus of 147 MB data extracted from Wikipedia, Arabic Wikipedia. And we have a complete vocabulary size, and vocabulary in terms of words, we have more than 500,000 unique words and almost 16 million running words. So it's a kind of reasonably big size corpus to evaluate these properties. So these are some of the results we get. So here we can see how much time it takes for training, and you can see word and morphology, interestingly, it's also expected, does not take a lot of training time, because word one, you can just use the idea of space and you can tokenize it. Morphology also is almost similar to word, but you can see character takes some time to tokenize, and again, it might look a bit counterintuitive because character, we just have to split it in characters. So why does it take a lot of time? The point here is that if you have a huge amount of text, splitting the word into characters and then combining them to place down the unique characters available in your corpus, it's also intensive computation-wise. So algorithm-wise, it's a very simple idea, but computation-wise, it takes a lot of time. A sentence piece actually is quite fast, and they have a very nice fast implementation of it. So does not take a lot of time here, we can see. But the most time is taken by stochastic one, because again, it's randomization. So every time you have to make that decision where to split. So it does take some time here. Once you have the tokenization ready, to apply it to unseen data, sentence piece is the one which takes the most time, because then you have a sequence of patterns you have to merge patterns. So you have to apply those patterns in a sequence. So it has to take time here. Word, again, as before, you basically have the same idea as training, just use spaces to tokenize it. Characters, again, because of the fact that there's a long sequence of tokens, to split the word into smaller units, it takes a lot of time to merge them. And the others are somewhere in between. The other thing is the compression factor. So we can see the character has the worst compression factor. So the higher the number, in this sense, of course, it's a bit, the figure is a bit counterintuitive here, but the higher the factor is, it's not compressing a lot. So, for example, let's take the word book. To give you an idea how we compress it. So book, what's the maximum number of tokens you can get by splitting them into characters or 4 characters? So the compression factor says that it's 4 out of 5 in a sense that 5y because you say the denominator is the total maximum plus 1. Y plus 1 because for unknown tokens, you have to consider that. So character would have a very high compression factor in a sense that it does not do a lot of compression. On the other hand, you can see sentence piece, it has the best compression factor in that sense. And word is also kind of reasonably good. Yeah. Then comes the unknown rates, and we can see that character and sentence piece have no unknown rates. Stochastics disjoint have very few unknown words in the unseen data. But on the other hand, a word and morphology does have a lot of unknowns coming. So this is something also, as we discussed before, we need to keep in consideration. Now we come to our supervised classification, evaluation on supervised classification. And as I said, the title suggests that the supervised classification we are doing basically on text classification tasks. And we have basically 3 different tasks. One of them is sentiment analysis as binary classification task. And we have used 2 different data sets for this. One of them is Arabic Jordanian general tweets data set from Mohammed et al. In 2017. This data set was released. And then you have large-scale Arabic book review data set, which is from Mohammed and Amir, released in 2013. So the AJGT, the tweet data set is a small data set. Why we selected 2 of them? Because both of them are binary classification, but the first data set is a very small data set. And it's on tweet data, which is not standard Arabic. So we wanted to also see the performance on a small data set and kind of not very standard Arabic. The other one is book reviews. It's more standard. The language is quite normal. And also it's a very large data set. So we'll see some statistics very soon for the data set. For news classification, we have this DSAC data set for Arabic classification from 2018, Denise. It's a multi-class classification problem where you have basically, if I'm not wrong, 5 different classes. So an article, a text, a news piece is either a sports, is politics, culture, economy, or is something diverse. So these are the 5 classes. Then we have this poem meter classification where we have the input is a verse. So this data set we are using is called metric. It was released in 2020 by Shergani and et al. It's basically our group. So we have 14 different meters in the poem. So each poem can, a byte of a poem can belong to one of the 14 different meters. So these are the different tasks we are going to evaluate on. So these are some summary statistics about those data sets. So you can see that AJGT is the smallest data set. We have on just over 11,000 words, right? So less than 12,000 words of the training. The metric data is close to 340,000 words. LABR is 762,000 plus words in the training. And the larger data set is the news one, which is more than 2 million words, the training data. Similarly, we have the statistics on the test data. And then the last 2 columns, we speak about the number of unique words and not the running words. And we can see that, again, it's kind of proportional to the data set size. So yes, AC has the highest number of vocabulary, which is in the training, you have 141,000 unique words. And the test is 27,000 unique words, and so forth. Okay. One more interesting thing you can see here is, although poem dataset is less than half of the LABR dataset, but the number of unique words you can see is very close to the LABR dataset, not too different, right? Again, this is because of the fact that in poems, people use very rich vocabulary, right? The language is not very common. So you have a lot of words which are very unique and that does not appear frequent. Okay, so before we do the text classification task, I'd like to introduce the general architecture we use for our deep learning system here. So what we do is we have these different tokenizers. So we run different experiments, 6 different sets of experiments, each time with a different tokenization scheme. And then these tokens are fed to the embedding layer, which is a dense vector, and we train that as a part of the training procedure. So we have embedding layer, then we have 2 layers of bidirectional GRU units, and then finally we have a dense layer, to give us the final output. Naturally, if you're doing a binary classification layer, the last dense layer is basically a sigmoid to do the binary classification. If it is something like news classification of 5 classes, we have a softmax with five possibilities and or 5 neurons, you can say, in the last layer. And if it's a poemeter classification, the softmax layer will have 14 neurons at the end there. And what we do is, once we set up this general architecture, we configure those parameters like embedding size, how big should be the embedding size, what activation functions to use, number of neurons in the dense layer, which optimizer to use. So normally we selected Adam, but we tried others also. Loss function also depends on the task you're doing and the number of epochs. So many of those parameters or hyperparameters were basically calibrated based on the results of the validation set. So we have a subset of the training set, we take it out as a validation set and see what those hyperparameters should be for those specific settings. So generally, this is the best type of setting we got is the 2 GRU layers with 256 units each layer. So GRU units each layer. The embedding size is 128 units. So Adam optimizer with 30 epochs of training. And of course, we leave it to train for 30 epochs, but we also save the best model based on the validation loss. So it need not be the last model, it could be any model between which has the best validation loss. We try to save that model for the final test. And we try different vocabulary sizes. So we said, okay, let's run one experiment where we have only 500, because there's something we also is a hyperparameter you need to decide. So in a given corpus, what should be, let's say we are speaking about words, how many unique words you want to keep, and what are some of the words you want to map it to unknown, because they are either very infrequent and you don't expect them to see again very often, so you want to map it to unknown, or they are so frequent, they are basically stop words, for example, fee, mean, and you don't, there does not maybe add meaning to the task we're doing, it does not influence your selected sentiments. So you want to decide based on that what should be your vocabulary size. So we tried these different sizes, 500 vocabulary unique words, 1,000, 5,000, 10,000, 20,000, and finally 30,000 as vocabulary size. Naturally, in some smaller data sets, you don't have that many 30,000 words, so we have to stop before that. But if the data set allows, we go till that level, And then because we have this deep learning systems, we can have different initialization. So what we do is, and the performance might vary a bit based on how you get your random start or your initial system start. So we do three runs for at least single set of experiment, and we average the results across the 3 runs. So these are some of the ideas here. Now let's see some of the results. So in the case of sentiment analysis using the AJGP, which is a very small data set, you can see that the best results overall, you can clearly see is the word tokenizer. So it's better than, like, it's above 80% accuracy in this sentiment analysis problem. And again, in the initial level, you can see morphological tokenizers are not is not doing so good in small vocabulary size. But if you increase the vocabulary size, it goes almost similar to word, right? And generally speaking, the lowest results are coming from the character tokenizer. And these results make a lot of common sense because if you think about character tokenizer and you have very little data, right? You don't have enough data to train those long contexts because characters are just single characters. So how do you, as sentiment, you're speaking about the meaning of is it positive or negative. So again, it might not be very easy to capture those meaning, even that you have very little data, right? And also generally speaking, characters will be very difficult to map to this context, right? And if you have a very small data set, then naturally words are the best thing to reflect sentiment because word itself can tell you what the sentiment is, generally speaking, right? So that makes a lot of sense that why words should work good in this data set. Now, this is another data set, which is the LABI data set on the same sentiment analysis problem from book review. If you recall, this is a bigger data set, quite big data set. And in this case, you can see still character does not do as good as others. But others, if you see high vocabulary size, big vocabulary size, almost all the tokenizers are performing very close to each other, right? So this is something interesting. And you can see sentence piece overall, if you see the overall trend, it does better than most others. Overall trend is that. But again, interesting to note that most of the tokenizers perform almost as good, especially in big vocabulary size. And because the data set is big,
you can have large vocabulary and still you have enough data to train it, right? And that also explains why word tokenizer still does good. Now, what about the another task, which is poem meter classification? So here you can see some very interesting trends. So on this data set, you can see that clearly character tokenizers are by far the best, and it's significantly different than other results, right? So character, you're getting above 90% accuracy, and the next best you're seeing is still almost 60% accuracy. So big difference between them. And the others are there, and morphological tokenizer is performing the worst, and even the word is not doing good. Maybe you can say, apart from character, the one which interestingly was somewhat reasonable is the stochastic tokenizer, because again, it splits into small words. The point here to note is what we learned from this particular experiment is that yes, it might also make difference depending on what task you're doing. Although all of them are text classification tasks, but you can see that some tasks, character, the first two data sets, we saw character was all at an average the worst performing one. But here is definitely the best, and not only the best. Yeah, I mean, the point here is that even if you want something reasonable, you have no other choice except by for going with character. And if you think why it's happening that way, there's a reason behind that. Because in Arabic, if you want to classify the meter, it's basically on it depends on the version of every character. What is the habitat, and it depends on the again, I'm no expert in poems, but at least I know a little bit that you have this you want to this Arudi form. You have this Arudi form, and you want to represent the text with diacritics on the Arudi form and see which words, which letters have pronunciation and which are sukun, sakin. And there is a lot of domain knowledge you need to classify it, but definitely you need to know the information at character level to know the meter. That's very interesting, and then that's the reason why we can see that character level performs quite good, right, in this data set. Finally, another data set was the news article classification, which was a high-class classification problem, and the data set also was very huge. This is the biggest data set we had in our experiments, and again you can see here. Overall, you can see the character is the lowest one, but in general, everyone is performing almost equal. There's small differences between them, but so the point here was that if you have a huge data set and you are not doing a task which is something very specific to the representation itself, then it might be that any tokenizer might work equally good. So this is something interesting also as a finding here, that you don't really see a big difference with tokenizer if you have a huge amount of data set and the task you're doing is not specific to the patterns you're looking for. For example, again, I'm just repeating that if you go to meter classification, and it's not only specific to meter classification, although we have not shown results of the other experiment, which is diacritization. So if you have Arabic text and you want to diacritize, the best tokenizer might be to use characters, because you need to decide the diacritics over the character. So you need those patterns for character sequences. So again, there's another task, which is adding dots to character. There are some in Arabic that also we did some experiments recently. We found that actually character is the best tokenizer. So what we conclude from these experiments is that yes, it could be that if you have a huge amount of data, then it might not matter which one you're using, at least for text classification tasks, except the exception being that you have a very specific type of task which needs some specific representation. So this is just a summary of what we saw. So we saw that a word tokenizer works good in the sentiment analysis. And another reason why that might also make sense is because, or if you think about other text classification like news articles, the topic might depend not on a single type of word. It depends on the collection of words belong to a topic. But sentiments is basically a word being a positive or negative. That tells basically that sentiment is good or not. So if you say something good, it's a sentiment by itself, or bad is a sentiment by itself. So word naturally works good because word itself can just reflect the sentiment directly. But then you saw that in metric, the poem meter problem, character was the best one. And in the news one, morphology although was the best one, but others were almost equally good in performance, right? So this is just the summary here. So yeah, to conclude, what we have done basically is in this work, we were looking at some mainly the upstream task of tokenization in natural language processing. And we compared 6 different tokenization schemes. The first 3 were commonly used in literature. The last 3, we
did not see a lot of work in that. So we wanted to compare those 6 different techniques for tokenization. And basically this work benchmarks this thing for text classification, at least, that what do you need to know as tokenization? Does it matter really that you have different tokenization schemes or anything can work? And we saw that it does matter in some tasks. Specifically, if you have a lot of data set, it might not matter. But then, you have to make a decision based on that. Now, it would be interesting, again, in this work, we have mainly focused on text classification problems. But what about, for example, machine translation? What about question answering or other NLP tasks? We did not do that work in this current study. So it's something interesting to pursue as a future work that, again, do same patterns, so same ideas hold for other tasks, NLP tasks, or more, it might be different. And also something similar we can benchmark for other languages and other scripts. So this particular work we did it for Arabic, but what about some other languages, right? So these are some conclusions and future work for me. Okay, so with that, I would like to conclude. Thank you so much. And if you have any questions, please let me. Thank you so much.
Okay, thank you, Dr. Ahmed, for your nice presentation. Now I will open the floor for questions. Please, for those who have any question here with us, please go ahead. And for those who the online attendees, please, if you have any question, please raise your hand or type your question in the question box.
Thank you very much for that good presentation, Dr. Simon. It was quite engaging. My question is that, can we please go back to that data set where you have the train implementation? This table. Yeah. I'm very curious. For example, the AJGT data set.
Right.
Is there any standard of splitting the training and test data sets based on the quantity of the data, or just doing random?
Okay, good question, actually. Yeah, what happens here is because these are public data sets, so many of those data sets you have this predefined splits. So people have been doing that. So they have a training set and the test set. So if it's predefined, we use the same split. If it is not, then we have this idea of like 80-20 split. So we go with 80% train and this, yeah. But again, it's a very nice question. But again, just to keep in mind here, because the idea here was not to for example, beat the best results in this domain, but basically to compare these different tokenizers. So whatever split you're doing it for all the other tokens. So in that sense, it's fair experiment. Yeah, but it's a nice question.
Thank you.
Yeah.
Thank you, Dr. I have a question about the stochastic type.
Right.
Since it's random, you run the experiment just anytime, then so the range of
Yes, we did. As I pointed out before, that what we do is, of course, it's a random decision where to split, and it can vary a lot depending on how you're splitting it. So at least we do 3 experiments for each single experiment. So if you fix our vocabulary size, let's say for words, how many words we need, and or for example, a data set, then you run 1 experiment, and then a second and third one, and then you have it.
It's very a lot.
In these numbers, we don't show the standard deviation of the results, but the idea here is bigger data sets, you don't see much variation. Smaller data sets, you have some variation. But you can always, you can report the statistical significance to see that it's really significant, the results are not. Because what happens in small data sets, you might have, let's say, 3% difference in accuracy, but that 3% is still not statistically significant because the results are small. Yeah, but you have some valid. Yeah, this.
Usually the form data set. Does it contain Harakat?
No, it does not. Actually, we had an earlier work in 2020, we published in Pattern Recognition Letters, where what we did is, the whole paper was about predicting the meters of Arabic poems using text which does not have harakats. Because in the literature, what we found out is that if you have text and you have harakat, then there is a way you can write an algorithm and you can even do without machine learning. Of course, then it's a long algorithm, it's tedious work, not easy, but you can do it. But what if in many of the literature you won't find those harakats? So we were thinking, what can you do if you don't have it? So in this particular data set, which we actually created with our students, Zaid and Majid,
we did not use harakats there. So we were relying on the deep learning system to learn those implicit relationships.
For Harakat, did you know the Harakat?
Yeah, we basically once we create the data set, we just crack out those things.
There is no specific organization. It is not.
Yeah, okay. Here, once we speak about tokenization schemes, harakats are not part of the text here in all those tokenizers, right? So what we do is basically most Arabic NLP, you do this text cleaning, and many times you remove the harakats. That's the standard practice. But of course, it's an interesting research to pursue that what if you have harakats and no harakats, and can you have different ideas and it can make a difference. But yeah, generally the standard practice is to just clean that.
Thank you very much. So can you back to the picture? Yeah. Okay. So now for the core model, what kind of you are using the BERT here? Or
No, these are dense embeddings. We train it as part of our task.
so is it possible to use a pre-trained model that we can move from?
Yes and no. The point here is because we have 6 different tokenizers, you don't have pre-trained models for those tokens. So you have, for example, a byte pair encoding, you might have it. For example, Arabic. If you're speaking about contextual embeddings, you might have Arabic. Or if you have, for example, words, you might have a word to vec for Arabic. Yes, but what about disjoint letter? What about stochastic one? What about characters? You might not have it. So you have to train. So to be fair, because if you use some pre-train and some over-training, it won't be fair comparison. So to be fair, we say that let's train each one of them based on the data set itself, just to be fair.
I have a question.
Sure, please.
Can you please go to the slide for the supervised evaluation?
Yeah.
Okay.
Maybe this one. Huh?
No, this one. For morphological tokenizer,
Yeah.
I think there are several morphological analyzer in Arabic, including Bakuma, Aramorph, and Khalid. Which one of them that you?
Yeah, we can check in the paper, but if my memory is correct, is the Farasa.
Okay. Another thing, I think it is the most challenging here for tokenizer is the morphological analyzer, because it depends on several lists as inputs. And you mentioned here the inference time here is the list for the morphological analyzer for this one. What is the more challenging one? Yeah, even here,
Yeah.
comparing with the characters and disjoint, still, and it is the more challenging
Right.
tokenizer is to use morphological analysis.
It's true, and that's why it's quite significant as compared to word. But once it comes to, for example, character, let's say sentence piece. Yeah, what you do in sentence piece, you have to run that merge operation in a sequence. So you cannot just do it parallelly. So sentence piece is the highest in terms of the time it takes for inference. But morphology, what happens is once you have the trained morphology, that you're going to apply that vocabulary on the test set. That's your vocabulary. So vocabulary is already defined in the training.
That means you didn't extract the prefixes and the
That's done here.
Yes, here.
In the training.
Yes. So this is my question
Exactly.
here in this slide.
Yeah.
Such task
It's
should be
pre-trained. It's pre-trained for us.
Mhm.
So you're using a pre-trained morphological analyzer. We are not training our own analyzer. That makes sense, right? So we are using a pre-trained morphological analyzer and applying it on our text to do the tokenization. So, yeah, but you're valid. And your point is valid that if you have a new text or new domain, or something is classical, something is standard, modern, then you might also have to think about training that type of system, which might take a lot of time. Yeah.
Another question, I think tokenization is a part, a task for as a pre-processing step for any NLP task.
Right.
And do you think is it still a significant task, especially when these learned based features like word-to-vec and the BERT and other based transformers still is it
relevant or no? Maybe it's not relevant.
Yes, because
Yes.
it is one of the aims or the goal of such techniques is to alleviate or to eliminate the pre-processing steps.
I completely agree with you. And that's the reason this work was done.
that because we see that one of the tokenizers we are using is this one, which is you're speaking about this byte pair encoding, all of this, which are popularly used in these deep learning models like Arab bird models and all these different bird models, Roberta and all these. They're using some variation of sentence-based tokenizer. So this idea is your point is valid that one approach is to say let's go language agnostic. So we don't care which script or language you're using as long as we have a tokenizer and which can learn the representation and we don't care about it. So you get the burden is lifted from the researcher because then you're just using an agnostic one. And that was the question. One of the primary questions we are dealing with this paper in this work was, is it good enough? The answer is yes and no. Again, you could go back to the results as one of the things we saw is this one. Go to the poem meter. So let's assume that I'm not using character tokenizer. I'm saying I'm just going to use DP or any sentence-based idea, right? And I just use those as a pre-processing. Let it do it. No, it's not going to do a good job. So in some tasks, the choice of tokenizer is important. Still, it's important. We cannot just ignore it, right? And in some tasks, it's not, but still there's a caveat. What is the point here is, if you have a big data set, then yes, those data that might work good, and you don't really have to bother about just that issue. But if you have a small data set, a very specific task, then it does matter which type of tokenizer you're using. So even after, I said that in the presentation. Poem meter classification is one idea, but digitization is another thing. There's few other tasks which heavily prefers character tokenization. But let's remove that even for the time being. What about other like sentiment analysis? If you have very small data set, word is still going to be better than other representation because the data set is small, you don't have enough training for that. So yes, it's a kind of a mixed answer that in some situations you're right, it's good to get rid of that burden, but not every time.
Another question?
Yes, please.
I think all of this, not all of them, most of them are accurate. Of these techniques are accurate 100% for tokenization, except the morphological tokenizer, because its performance or accuracy based on the algorithm itself. Do you think this bias affect the results or the conclusion in this presentation?
Definitely, you're right. The point here is the morphology, again, unless you have a perfect morphological analyzer, your results might be a bit different here and there. And again, the goal of this work was not to compare different morphological analyzers, but you're right. Again, if you change it to a different morphological analyzer, then you might get a bit different result. How different is, again, we didn't do, so I cannot give a number to say that, really how much it is. But at least what we did in our work was we selected one of the best available in the market. Because the point was to compare morphological one with different ones, not to compare between different morphological ones. But you're right that, somebody can say, let's see really the difference on different tasks of if I'm using this morphological analyzer versus something else, and how big difference does it really make? Again, we didn't do that work, but it's a valid point to pursue if someone is interested. Yeah.
So then I have more problems. Thank you, Mr. Arfan, for giving us the time. I'm a late comer, so I'm not giving you a technical question.
And I can always choose that I did that once you were not there, right?
Yes, it's. I believe now Arabic NLP in general is gaining attention, okay? Gaining a little bit of momentum. And the question that I personally is where do I start? How do we stand from a data availability Arabic NLP in general? What are the resources? What are the efforts that we need to have a large language model similar to the one that was recently done, GPT, what is it? Something like that, where we have these kind of impressive language models in Arabic. Or we already have all the resources, it's just a matter of research. Can you comment?
Okay, again, from my perspective, or let's say limited experience in the area, I have few comments here. One of the things is definitely that what has been done for other languages, one way to pursue is to do something similar to Arabic. For example, you have a GPT-based huge language model. You can have something for Arabic similar. For example, you have birds, you have Arabic, and that's a valid thing to do. But I personally feel much more interesting and valuable research is, especially for our region, is to focus on the language itself. Because if you are doing something which others are doing and replicating it for Arabic, it's definitely there is some value to it, no doubt about that. But it's limited because then you're just replicating an idea.
and it's useful. But if you use the language peculiarities, language specificity to come up with new ideas, which is only applicable for that, and that might work better than the standard approaches, then I think that's where we can use our, for example, skills and experience, because in our region, not everyone can look at the script or language and understand what can be done, except those who are familiar with the script. So I would say that, yeah, of course, collecting data sets is very important. Doing replicating other popular studies and making those resources available for Arabic is very important. But at the same time, we should focus on things which are very specific for the language itself, instead of just going with standard.
But what about the data availability? How are we doing? How is Arabic doing?
Okay, yeah, that's again interesting. People, there are efforts, but unfortunately they are isolated efforts. So people are doing, different groups are there, they are collecting data, they are making data public. It's a big effort going on, but there's no very huge joint effort in data set collection. That's true, and that's something I guess as the community we have to look into it. How we can, for example, coordinate the effort to make sure that instead of everyone doing something and making it public, why not make a joint effort and make something quite big as compared to what we can do individually. Again, even in our small group where we have, for example, Majid is there working with me, Zayed is there, we are having some very interesting repositories for now for Arabic. It's not only the data sets, we do have a lot of data sets, and interestingly, our students, they are also creating very user-friendly APIs to access them in different formats. So we have exactly just say which tokenized form you need, and you can just give this API request and you can get that data set in that format. So they're working on that. They're doing two, at least from our group perspective. They're creating libraries for Arabic specifically to use. You don't have to reinvent, so to say. And they're also making a lot of data sets. They're scraping from around the web or whatever public resources we have, and we are standardizing it, cleaning it, and making it available for the researchers. So those efforts are there, but of course, as I said, these are small efforts, and again, if we can coordinate across different research groups, that definitely can be.
One last small question, if you don't mind. Given that we have a lot of books in Arabic that can be easily translated into digital text, I believe this would give you the roots of the language, would give you insights of the language spoken. But if you compare that language with the language that we currently speak, these are different. Is this a challenge by itself in Arabic, or does it exist in other languages? For example, in English, and do you believe that this would be a barrier to gender? This formal and informal.
Yeah, this is definitely it's you see this type of challenges are common to every language, but these specific challenges are specific to specific languages. For example, again, let's go back to Arabic. You have what we, again, one of my students recently, he worked on this topic of give me a paragraph of text and I try to predict which era this text comes from. Is it coming from Jahiliyyah? Is it coming from Islamic? Is it coming from Abbasi? Is it coming from Andalusi? Or is it a modern text? So, for example, and again, now you have these, and these are still standard Arabic in a sense. Of course, some are classical, some are modern or standard. But then you have text like Twitter, text like reviews in apps, right? These are not necessarily even standard text. So how do you deal with them? You have dialects. So you have Maghribi dialect, you have Khaliji, you have Shami, you have all these different dialects. So is it becoming a challenge? Yes, it's a challenge. That's the fun of research, right? So these challenges leads to new opportunities. So people are working on these areas. So people are, for example, creating data sets. You have multi-dialect data sets, or people are coming with specific ones. So both of them have uses. So you also want specific, very precise data sets on very, let's say, a uniform, homogeneous type data set that its own use. And you also need heterogeneous data set and try to compare whether, for example, transfer learning might work or pre-training might work or not. So yeah, these challenges in a very broad sense is applicable to any language. English, you have Shakespeare English, and if you apply that to a modern English, it's, we might not understand maybe 20-30% of text, right? So I remember in school days, one of these courses in English, we have to take a Shakespeare novel. That was one part of the school. So in English, and it was just a struggle, but again, that's how it is, right? So yeah, so the challenges are there. I'm sure about German, because I did my PhD from there. I know I went to a very old library in Germany, and we saw this old German script and old German text, and it's quite different than the modern. So those language challenges are there. Again, the specificities are language. It depends on the language, but generally speaking, those challenges are there.
Thank you, Dr. Ahmed, and thank you all for attending our today webinar presented by Dr. Irfan Ahmed and organized by Sedaya KFUBM Joint Research Center for Artificial Intelligence. And looking forward to seeing you on our upcoming events, inshallah.
Thank you so much. My pleasure.